Hello everyone. We are going to solve some of the problems in the exam 4, which covers chapter 1, 1, 2, 3, over problem 2. Okay, so now let's start with problem 2. The problem states the bowl, aluminum bowl, holding soup at the temperature, and now is placed in a freezer. That means the temperature will be cooled down. If this total energy is transferred from the bowl and soup and etc., and what is the final temperature? That was the question we need to answer. So we need to check out what data are given, the mass of the soup, which is taken as a kind of water. So this we used MW water, and then it is 0.8 kilogram. Aluminum bowl has this mass, and then it is as of aluminum. Initial temperature was this, and then in the freezer, the heat is removed by this much. And the thermal data is the specific heat of water, ice, and aluminum, and the fusion, latent heat for the fusion for water and ice is given by this one. So we will check out with this amount of heat removed is enough to cool soup and bowl from 21 degrees C to 0 degrees C. And then what is going to happen is that at the 0 degrees C of water, which is soup, it is going to be freeze into ice. So here we are going to utilize the latent heat. And then after that, cool the ice, once ice is formed, and then the rest of the heat is removed to cool the ice and bowl. So initially it is water plus bowl, and then temperature is reduced, and then water becomes ice, and then ice plus bowl will decrease delta T. But as you know that in the case of this case, T is 0 degree, and furthermore, you can decrease the temperature like this. So it's a kind of a 3-step process. So let's try to find out what is going to happen if we cool the water and the bowl from 21 degrees C to 0 degrees C. And then we note that by the heat transfer, such that Q is given by mc delta T, the mass of the material, and the C is the specific heat of the dead material, and the temperature changes. So here we have a delta T is known, and then for the water, specific heat is given, and then mass is given, and then for the water, we have this amount of energy. And for the aluminum bowl also follows the heat transfer, so that mc delta T, so that we get this much amount of energy. So total energy to cool to 0 degrees C is that Q1 is given by this much, and then you have this much about joule. And then note that we are given quite a lot of here. 360 kilojoule. It is 360 times 10 to the 3 joule. 360,000 joule. So now we have a 74,000 joules. So that is still we have much to go with it. Okay. And step 2 is to freeze the soup at 0 degrees C. Note that there's no temperature changes, but you have to utilize the mass of water and its latent heat fusion. And then these values are already given, so that you have a Q2. And then now water is ice, okay, after step 2. And then the step 3, we need to check whether Q1 plus Q2 is, how much is it? And then Q1 plus Q2 is this much. And then energy is still available to remove. Is that Q total is given this, and then we have utilized this one, so that this much of the heat can be furthermore removed. That means now ice and the aluminum, not the water and aluminum. Now it's ice and aluminum will further cool down. Okay, so we are going to have the total capacitance. So now ice and water will have a both solid, okay, solid, such that we have a total capacitor, heat capacity is given by mass of ice and the mass of aluminum. And then this is what it is. And cooling from 0 degrees C down to TF, which is, we have to find out. And then Q3 is this one. But you don't have to worry about this much, but actually it is nothing but M ice, C ice, delta T, plus Mr aluminum, C aluminum, delta T. So it is, you can have a delta T factory out, and then you can get this one. But you can do it individually. But anyhow, what we now know is that we have a leftover energy Q3, and that this should be equal to this. So that we have final temperature is given by this much. Okay. And then the final temperature in Kelvin is now note that this is the 0 degree, and it is going to be further cooled down to this much, so that we have this one. 0 degrees is nothing but 273 Kelvin. So you have to follow the logic step by step. So you need to cool the water and aluminum to the 0 degrees C, and then the water turn into the ice, and this both ice and aluminum is further cooled down, and then it should be converted into the temperature Kelvin. Okay. Now this is result of a thermal expansion. So L is actually alpha L0 delta T. Okay, so that was the thing we need to consider. And then this is the thermal expansion coefficient. And then what is happening here is that there's some kind of crack in the beginning, but as the temperature goes up, and then these are expanding, so that this is break up like this, and then it turns into kind of a triangle, and then we need to find out this x value. Okay, so in order to do that, what you have to do is that we start with the total length. Here, so L is given, and then half of them is L over 2. L over 2. And then this is the L0 initial length, and then this is what it's given. And the linear expansion is given by this one, and the delta t is given by. And if it is free, each half would expand to a length like this. Okay, this is what we get. Okay, so note that L0 alpha delta t is delta L. So that means L0 plus delta L. Okay. So this is the how much length is added by thermal expansion. So we have this L, and then what we have here is that so I'm just exaggerating. It's L0. So by expansion, now it's a split, and then it is split by half with this length. And then we have this trigonometric case, okay? And then note that L0 is 2 over L. So this is the L0. From here to here is L0. And here to here is L0. Okay. So in this triangle, you have this one. This is the and then you get these equations, and then eventually you get this x, and then the L is given by this one, and then if you just plug in, then you have x is given by initial length, thermal expansion coefficient, and the delta t. And then you can numerically find the answer. So now what is going to happen here is that we want to cool water at initially 20 degrees C by adding ice. And that ice was initially this temperature. And then the question is, how much ice should be added so that the final temperature will be 0 degrees C with all the ice melted? Okay, that is the important one. So let's try to understand what it is. The heat lost by the water cooling from 20 degrees, 22 degrees to 0 degree. So mass of water is given by this one, and then specific of heat was given by this one. Temperature change is this one. For the water, we get the heat transfer formula mc delta T, and then this is what is going to be lost. The water becomes 22 degrees to 0 degrees for the water. And now heat gained by each kilogram ice, the ice starts at the minus 16 and at liquid water. So this is the very important one, liquid water. And then warm ice from minus 60 to 0 degree. We note that specific heat of ice is given by this one, and the delta T is given by this one. And this is how the ice is reaching temperature from minus 16 to 0 degrees. Okay. So here we have we did not put the m here because it is the per kilogram. So initially we should have a certain m of ice, but we are going to find out what they are. Okay. And then we are going to assume the unit each kilogram, so that 1 kilogram has been assumed. If it is 1 kilogram, we have m equal to 1, okay, and then this is the 1. And per kilogram, so we have this per kilogram. So melt the ice at 0 degrees C. So note that ice is still ice. Now it's going to be water. And then in order to take this phase transition, we need to have a latent heat over fusion. And then per kilogram, we have this one. So the total heat absorbed per kilogram of ice is that you let the ice warm -16 to 0 degrees C ice, and then you melt the ice at 0 degree to the 0 degree water. And then this is what we get per kilogram, okay? And then we are going to set the mass of the ice to be added. So what is going to happen is that if you just multiply Mi per kilogram, then we should equal by energy conservation. This is the water energy lost, and then this should be the energy gained by the ice. Okay, and then this is the final question, final equations, and then you can find the ice mass. And calculate the absolute temperature of temperature of a lead ball after it falls from the height of this on the floor without bouncing up, so that all the energy of the fall goes into heating the lead. The initial temperature of a ball was this, and heat capacity of this is this given by, and the gravitational acceleration this. So in this case, what is going to happen here is that energy conservation is applied. So initially, it had a certain energy. So it had a certain energy with the H. And then it falls here. And then it doesn't bounce, so that all the energy is generated heat. Okay, so let's try to find out the potential energy. Is obviously this is the mgh. So we get this gravitational energy, and then this is going to be changed to the heat transfer, and then Q should be mc delta T. We know that what Q is, it is nothing but this. So the first thing is that the heat transfer, Q is in fact energy, joule, right? So that in this case, potential energy of this ball is now changed into heat, so that the potential energy is now changed to heat. And then we can find out the delta T. And then you can get the delta T like this. Now, block of ice at 0 degrees, whose mass is initially given like this, and slides along the horizontal surface, starting at the speed of initial speed is given, and finally coming to rest after traveling a certain distance. Okay, compute the mass of ice melted as a result of a friction between the block and the surface. So once again, this is another assumption that this is the ice, and it is given with the initial velocity. And because of the friction between the ice surface and the surface of this bottom, and it travels a certain distance and then it melts. like a kind of water, ice. And then we need to find out the mass of ice melted as a result of the frictions, water, and some of them would be still ice. Okay, so now let's see what is going to happen. So mass of the block was initially this, okay? And initial speed is this one. That initial speed means note that it is sliding around the surface. There's no change in the height, so that it is changed in the kinetic energy only. So initially it had this kinetic energy, is now, and then what we have to think about is that the melting is happening. Then when ice melt, we have to use this latent heat. And then if delta M is the mass of ice melted, delta M, mass of ice melted, then we get the heat is needed this much. And this is the heat it is needed to change the ice into water by this mass. And then by energy conservations, the kinetic energy should be this heat. Okay, and then we can find out delta M. Okay. So 100 kilogram weight is hanging from the ceiling by a thin copper wire. In its fundamental mode, the wire vibrates at the frequency of this. You then increase the temperature of the wire by 29 degrees C and find the magnitude of change of a fundamental frequency. Coefficient of linear expansion is given like this. So that what is happening here is that here is the ceiling, and then there is a mass, 100 kilogram. Okay. So this will give you a certain tension. Okay, tension. And for the given mass of copper wire, and then we have mass density, linear mass density, and then we know what the velocity is. So velocity is and then we found out that it's a fundamental mode. That means we get the wave. This length becomes lambda over 2. Okay, right? And then the velocity should set, if this is a wave, velocity always satisfy lambda times f, the wavelength of this one. And lambda is 12 f. Okay, and then we all talk about the frequency. The frequency is given by, well, I'm sorry, this is T. T of mu. This is what we have found for oscillations, right? And now what is going to happen here is that by changing the temperature, this length is changing by linear expansion here. Once length is changing, then we get everything is going to change. First thing is that wire's linear mass is linear density is going to change. Initially you have a this, now we have a mass does not change, but the length changes. So that we have a, this is new mu prime, okay? And another thing is that we have a length change and the linear density change. Linear density and the length change will result in the new frequency. Length changes, change the length and change the linear mass density. And then take the ratio like this and then substitute. And then the frequency is going to be changed into this format such that we get this one. And we know what the alpha is, we know what the delta t is, and then f prime is going to be this factor, okay? And then if you calculate this one, then eventually f prime is going to be this one, okay? Delta f, but the question is change in the frequency, delta f. So that means the changed frequency minus initial frequency, okay? So that is final answer. So this problem is interesting because it combines the wave on a string, and then we are going to change the temperature, and as a result of a changes the temperature, we have two effects. First thing is obviously the length is going to be expanded, and this will change the linear mass density. And then this will, this L prime and mu prime will change the frequency. That's the key thing you need to keep in mind. And then once you get the F prime and then minus F is what we want to have. A major source of heat loss from a house in the cold weather is through the windows. Calculate the rate of a heat flow through a glass window 2 by 1.3 meter in an area in A, and the D is 3.4 millimeter thick. This is the A's area is given and the D is given. And we have a T2 and T1. So outside and inside, for instance. T1 is 16 degrees C and the T2 is 13 degrees C. And the thermal conductivity of the glass is given by this one. Then what we have to think about is that the heat transfer have three passes. One is the conduction, convection, and the radiation. For the conduction, we have this formula. Here the P is power. Okay, energy divided by the time. Okay, so it is given by this thermal conductivity, area, and the distance, and this temperature difference. So once you memorize this one and then try to apply this formula to this situation, then the problem is fairly simple. You know what the area is, and you get the P, and then that's the result. And then we can find out how much it is, okay? And 21 is a little bit furthermore application of a thermal conduction. So we have three different metal here: copper, steel, brass. That has a different type of temperatures as well. So what is going to happen is that the heat will flow by conduction from the high temperature to low temperature, as indicated by these arrows, right? Okay. And then, but the problem here is that the three material have a different thermal conduction and the different lengths. So copper rod at the end 100 degrees C and the length is given, and brass 0 degrees C length, and steel 0 degrees C and the length. And all of them have a same cross-sectional area. And the thermal conductivity of copper, brass, and steel are all different. And let the junction be temperature of T. So T at the junction. So question is, what is the temperature of the junction point? Okay. So what we have to think about here is that, once again, it is based upon conduction. Okay. So we get heat current, or divide the time, is given by this one. Area and length and the delta T. So area was all the time same. So copper rod from 100 degrees C to the T, and then T to 0 degrees C. So what we are going to assume is that because all of the materials are combined here, so this T is assumed to be same for the steel at this position, same for the copper at this position, and same for the brass at this position. So copper will cool down from 100 degrees C to T, and then furthermore, steel will cool down from T to 0 degrees C, and the brass will cool down from the T to 0 degrees C. So what we are going to do is that for the copper, heat conduction is given by this one. From T to 0 degrees C, brass rod, where the brass is given by this one. Steel is given by this one. Okay. And at a steady state, heat flow into the junction equals heat flow out. Note that the heat is flowing to this one. Okay. So here's a PC, PB, or PS. Okay. And then we should have a conservation of energy in a sense. PC should be same as PV plus PS, right? And then sort of for the equation for the T, we get the equation for T like this from this requirement, and then plug in the numbers, and then we get the temperature. Okay. And then it should be converted into the Kelvin, and then this is our final answer. Okay. And 27, air bubble at the bottom of a lake, 27-meter deep, has a volume of 1.4 cubic centimeters. Note that it has a volume. If the temperature at the bottom is this, and the top is this, what is the radius of bubble just before it reaches the surface? Normal atmospheric pressure is given by this one. Okay. So let's try to understand what is happening. So what is happening here is that initially, this is water. Initially, this is the bubble. Okay, it has a volume initial. And then as goes up, it's going to be this one. Okay. So the reason why it is changing the volume is the temperature is changing. Okay. And then we note that as the bubble rises, both pressure and the temperature changes. So PFI. And those things, let's say this is the 2, state 2 and state 1. And if it is ideal gas, we have this relationship. So inside is filled with ideal gas. Okay? And then this should be satisfied. And then let's try to find out the bottom of the lake. H is given by this one. And the pressure at the bottom is given by P1 equal to P0 plus rho GH. If you look at it, this is the pressure is actually the force divided by the area. Okay. So force in this case is actually the water. Water is going to give you the additional pressure. So initially, atmospheric pressure is this, and the water will increase the pressure. So as you go deep in the water will give you the additional pressure, which is actually the mass of the water is giving you additional force. And this is given by this one. So in other words, if there's a certain area is given this. H. And then the amount of the water that corresponds to this column, which is rho times GH, actually time A, is gravitational force on this area. And the force divided by the area is pressure, so that as you go down, then you will have additional pressure due to this gravitational force. Okay, this is the one thing you need to understand. So this is the very important step to solve the problem. Then, so we have a pressure at the bottom is given by this one, and temperature is at the bottom is already given. Okay, and then and also we have a initial volume. So we know what the P1 is, we know what the T1 is, and we know what the V1 is. And then what we have to do now is that we are going to, before reaching the surface now becomes the atmospheric pressure. And at the top, we have a T2. I want to find out the V2. So that we have a P1, V1, T1 is known. We know P2 and the T2 is known. Then V2 is given by this one. And you can find out volume. And then volume will give you, because it's a sphere, so that R, and the V is, volume of sphere is given by this one, and such that you will end up with the radius, okay? And helium and oxygen molecules, and the Newton mean square velocity of oxygen molecule is this one. Now we are going back to ideal gas. And the molar mass of helium is this one. Molar mass of oxygen is this one. The universal gas constant is this one. Find the temperature of a gas in Kelvin. So what is happening here is that molecule velocity is given, and then find out the temperature. So we are going to change the molar mass of oxygen is going to this one, and then we are going to change the kilogram. And then we all know that root mean square of ideal gas is related with this temperature. And then from the this relationship, we can find out what the temperature is. And then we from the given number of root mean square, and then we can just plug in T here. Note that mass is a molar mass. Yeah. Okay. Root mean square velocity is this one. And then we have a ideal gas constant is given by this one. And then we can find out T. Okay, so relatively easy problem. Now, this is the interesting one. The escape velocity from planet X is known. And what temperature would hydrogen molecule have a root mean square velocity equal to planet X's escape velocity? The universal is this one. That means the first thing is that you need to correlate the root mean square, okay? And then we need to find out the temperature actually. So everything is changed into a proper unit, okay? In Kelvin, m is kilogram per mole. And then importantly, this root mean square is given like this, okay? So it's escape velocity, okay? And then important step is that you have a molar mass. So H2 molecule, so you have this value. And then once you plug into this one, then you get the T, okay? Uh, a vertical cylindrical tank contains 1.87 mole of an ideal gas under pressure of 1 atm and at 20 degrees C. The round part of the tank has a radius of 10.8 and the gas is supporting a piston that can move up and down in the cylinder without friction. What is the mass of this piston? So that what is happening here is that tank has a radius R given, right? And then there's the piston. And it can move up and down, okay? And we want to find out the mass of this piston that is supported by this gas, ideal gas inside, okay? Uh, so that at the most, assumed a vacuum in the tank above a piston, so that above pistons the pressure is vacuum, okay? And then what is going to happen is that the vacuum of the piston inside tank, the only force in the vertical direction on the pistons are upward force from the gas pressure to the area upward force. And then there is a downward mg. Then that means there is no other pressure. So pressure outside of the piston, upward piston is zero. So that all, whatever happens, this is the only upward or pressure will be exerted, and then it is balanced by the gravitation. And then that means at the equilibrium, the pressure inside will give you this force upward, and then this is going to be force downward. And then we can find out m is going to be this one. And we need to find out area, and the radius is given so that the area could be pi r square. So we can find out area, and then the we note that the pressure, area, and the gravitational force, acceleration, and then we can find out the mass. And now let's try to think about a flask within a with a volume of 1.4 liter provided with a stop cork contains an ethane gas at 290 Kelvin and at atmospheric pressure. So pressure is given, volume is given. And molar mass of ethane is this one. System is warmed to a temperature of 385 K. So initially this temperature and goes up to this one. When stopcock open to the atmosphere, so that means there is a so initially ethane is here, T1, B1, P1, and then it's heated up so that T2 change it. And then note that the pressure here is open, so that means pressure is also P1. Okay. And then now it's changed to the situations. Once you heat it up, and then it changed to we have this clock, and then cool down. So it changed to the T1. And then we are going to find out the mass of ethane remain in the flask. Note that there should be so volume initial is volume of flask is given, T1, atmospheric pressure is given, final temperature is given, and gas constant is given. Then what is should be known is that the amount of a gas initially in the flask. So that the ideal gas law says this one, PV RT, so that this is the number of molecules and or mole. If it is PV is nRT, then we have N is given in terms of a mole. And the heating with the stopcock open, the pressure is fixed. So pressure is open, so that means the pressure is 1 atm, but the temperature changes. So that we have another PV in these cases. So you should this time you should have a N2. Okay, so N2 is given by PV over T because temperature is changed so that N2 should be changed. Okay. So in other words, volume is fixed and the P is fixed. Okay. And then cool back to 290 K. Now this is the stopcock is closed. Okay. So what is happening is note that N2 it start from the N1 and then it changed to N2. Okay. So the question here is that the question asks for the mass of ethane remaining. So that we just use N2 times molar mass. And then we get this one. Okay. That's what is happening. So what is really happening here is that as the temperature goes up, some of the ethane gas is going to leak out. So that's the reason why we get the N2 is changed. Okay. So as a temperature T1, so volume is the same. Then inside the flask, so it initially is N1 and then N2. Okay. So, some of them has just left the flask. Okay. And then we just close it and then find out the mass. And this is what we get. Okay. calculate the number of molecules in the air in one breath with a volume of this one. Temperature, pressure is given. Okay, and then we note that ideal gas will have a PV and KBT, and this is for the nRT. So we have all the things so that the number of molecules will be utilized. This one. This is N is a mole number. And then in this case, is the number of a molecule is given, and then you can find out N. Okay. Calculate how much time in average it would take an oxygen molecule to move back and forth across the 6-meter long room 40 times. So if you think about this one, so first we change the temperature in the Kelvin, and then what is given here is that time in average, and then there is a distance 40 times. So that means so this will give you the total length. And then what it asks is that basically you want to find the velocity to find the time. The distance is given and the velocity is known. It should be v times t, time. Okay. So in this case, this is the ideal gas, so that we have this relationship. And then we can find out the root mean square velocity of this oxygen molecule. And then total distance is one round trip is 12 meter. Round trip is 40, such that we have a total distance this. However, problem statement says that passing in total 240 meter distance, so 240 meter. So total distance is given 240, so that we get 240 meter divided by this one. So there's something wrong, but the important thing is that this distance. So distance is given, velocity is known, and then we found out time. Okay. Okay, thank you.